What's going on, everybody? It's Mr. Gustin in the chemistry classroom. We're talking about nuclear decay today and the particles that we've discussed in class and what they do to a radioactive nucleus when they are emitted, why they might be emitted, and so on and so forth. So we've discussed two types of particles that may be emitted from a nucleus. Now, the reason why a nucleus may or may not undergo radioactive decay has a lot to do with the mass of the nucleus. We've watched the video, we've talked about the strong force and what holds the nucleus together. But what tends to happen is that if atoms or nuclei get too heavy, or they have too many protons and not enough neutrons in their nucleus, they become radioactive, they become unstable. And when they're unstable, they emit particles that allow their nuclei to be more comfortable or be more stable so that we aren't at risk of falling apart. Okay, we talked about kind of the violent nature of the creation of nuclei through fusion in stars. And so once those nuclei do fuse, some may be stable, some may be unstable. And it's the unstable ones that we're looking at here today and have been looking at in class. So let's talk about the two particles, particularly the two particles that we discuss in class and what they might do to the nucleus. So we've seen two. The first one we've seen is the alpha particle, spelled alpha, A-L-P-H-A, alpha particle. It's denoted by the Greek symbol for alpha, or A, or like a Jesus fish, if you will. But alpha looks like this, and the alpha particle has a mass of 4 atomic mass units, and it contains 2 protons. So if it contains 2 protons, has a mass of 4, what that means is it's made up of 2 neutrons and 2 protons. It's essentially a helium nucleus. So why would a nucleus emit an alpha particle? Well, it would emit an alpha particle if it is what we call too heavy. If for some reason there are too many protons in the nucleus and it is too heavy to remain stable, we would see this thing eject or emit an alpha particle that would allow it to move itself back towards that 1.5 ratio of neutrons to protons. We've looked at the belt of stability, but this is what an alpha particle does. It tends to change the mass of my nucleus. If my nucleus is too heavy to be stable, alpha particles tend to be ejected. The second particle that we've discussed is the beta particle. And a beta particle actually has no mass. It doesn't change the mass of my nucleus. It changes some of the particles within the nucleus. So a beta particle, written as a capital beta, Greek letter beta, has no mass, and it doesn't eject a proton. It ejects a charge-carrying negative particle of some kind. So it actually has, we say, -1 protons. Basically, think of it like this. If a neutron consists of a positive charge and a negative charge, making it an overall neutral particle, that negative charge gets ejected in the form of a beta particle. And what we're left with is a new proton. So, if for some reason my atom has too many neutrons and not enough protons, it's heavy and unstable, but it needs to be held together by more protons, we might see a beta particle being ejected. So beta particles change the number of protons in my nucleus without changing the mass, whereas the alpha particle changes protons and also changes the mass. So these are the two big particles that we've talked about. There are others out there as well. We have positron emission, which is kind of the opposite of the beta particle emission. But these are, we also have like electron capture, which is like the exact opposite of beta particle emission. We have all these kinds, but for our class and for our purposes, we're most concerned with the alpha particle and the beta particle. So what we're going to do today is look at an example of what we call a decay series. We'll take a radioactive isotope of uranium, uranium-235, and we will go ahead and work our way through a series of alpha particle ejections and beta particle ejections to see what isotope we end up with. We're going to kind of practice these things over and over again. And I've got 1, 2, 3, 4, 5, 6, 7. I've got 8 different particle ejections that we'll see, and hopefully that practice will allow us to get better at nuclear reactions. So here we go. Let's get started. Again, so these are nuclear reactions, not chemical reactions. So they're written similar to chemical reactions, but we use isotopic or nuclear notation instead. So we start with uranium-235. That's uranium with a mass of 235 atomic mass units. That's the mass of uranium. And then we also want to make sure that we denote the number of protons. So I go find uranium on my periodic table, and it ends up being element number 92. So it has 92 different, 92 protons and a total mass of 235 atomic mass units. So if I got the calculator out real quick, I would do 235 minus 92, and it would tell me that it's got 143 neutrons in there. Now, does that matter? Not really, but it's something I could know and I could do in my head on a calculator rather quickly. So let's see. The first type of radioactivity or particle ejection is an alpha particle ejection. So uranium is a radioactive isotope. It is going to undergo some kind of nuclear decay, and when it does that, an alpha particle gets emitted. An alpha particle has a mass of 4. It has 2 protons, and there's the particle there. So because this nucleus ejects an alpha particle, that means it's losing a mass of 4, 2 neutrons, 2 protons, and like we said, there's the 2 protons right there. It's also losing 2 protons. So what's left over is going to be an isotope or a nucleus that contains a mass of 231 atomic mass units. Why? Because 4 of them are tied up in this alpha particle. And then the new identity of my element is no longer uranium. It's uranium minus 2 protons. And if I come over here, uranium is 92. Element 90 is thorium. So I'm left with element number 90, thorium. And this is my new isotope. We call this a daughter isotope. Daughter isotope is an isotope that exists after some kind of radioactive decay. And so after the first decay, thorium-231 is the isotope that's left over. So I can check that off my list. I did 1 alpha decay. Let's go ahead and do beta decay. Beta, I'm starting with the thorium-231. It has 90 protons. There's thorium. It undergoes beta decay, which doesn't change the mass, but it does change the number of protons. And remember, the beta particle has a -1 proton. That's weird. Really, it just emits a negative charged particle from the nucleus, resulting in a gain of protons. So I see no longer does my nucleus have 90 protons. Now it's going to have 90 plus 1 protons, which bumps it up to 91. So I'm going to have 231 as my mass number, and element 91 is going to be my new isotope. My daughter isotope is this element 231. So there's my beta. Next is an alpha. Let's try alpha. So I got 231, Pa 231, element 91 undergoes alpha decay. And alpha decay means I lose a mass of 4, so I'm at 227. And my new isotope is now no longer element number 91. Now it's element number 89, actinium. And we can go on all the way through this step. We would lose an alpha particle. Let's do it again. 227, 89 from my actinium daughter isotope. I lose 4, 2 alpha plus whatever's left. So 227. It ejected 4 mass units, so I'm left with 223. And then my new element, it's no longer actinium. Now it's going to be element number 87, which can be found right here. Francium 223 at 87. Now, again, francium is the new daughter isotope. Let's do one more beta decay just to see how that works again. And then we're going to wrap this video up because we've done a bunch of decays of the 2 particles. So the last one, we're starting with francium 223, element 87. We're going to emit, that should be a lowercase r, we're going to emit a beta particle. Again, beta particles do not change the mass of the nucleus. They only change the number of protons and neutrons in the nucleus, right? So I would lose a proton, neutron, I'd gain a proton. That's what's happening here. So the beta particle is emitted. When it's emitted, I still have a mass of 223, but because I'm losing that negative charge out of a neutron, that neutral neutron now becomes positive, a proton. Because that happens, this number of protons goes from 87 up to 88 and becomes radium. It goes from 223 to 88. And radium-223 is my daughter isotope. Now, folks, this type of decay will take place over and over and over again until this nucleus becomes a stable form of an isotope. So we would go through this decay series over and over again until it reached one of those stable isotopes in our series. Okay? So this is the alpha particle, the beta particle. This is nuclear decay. This is how I might think through a decay series problem. We talked about what a daughter isotope was, how we can identify it, and how that daughter isotope then becomes my isotope that undergoes either beta or alpha decay. All right? If you got questions, email me, let me know, but this should be enough to help you get started on some of your nuclear decay series practice. Until then, see ya!